Well, maybe there will be next week, Tuesday or Wednesday. So we're working all through these. You have the problems from the homework in the textbook. Some of those are not word problems, like 1 through 4. So there's probably going to be one along those lines, similar to like the very first example, not the cone, but the first like just generic XY stuff that we did on Friday. And then I have a whole nother packet of like 25 more related rates problems. We're not going to do all of that, but I'm going to have that. We'll pick and choose from among those. It's like another homework assignment, more stuff in class, so that we really kind of have a chance to digest this stuff, because it's deep, it's hard. So the more you see it, I'm not going to pretend it's not hard. It's hard stuff. So the more we see it, the more comfortable we'll get with it. But it takes a while to get there. So that's why I'm ready to devote like a week and a half to this. What's tough about this is it kind of draws on all the math we've done up to this point, not just in calculus, but like also geometry, also your algebra. Like everything is now coming together into one topic. So there's a lot that's going on with it. All right. Secant is 1 over what? Okay. Blank plus 1 equals cosecant squared. Yay. And then this is what we were doing on that previous quiz with getting dy dx by itself. So 3x squared becomes 6x. 2xy is product rule because you have 2x times y. So derivative of the first guy is 2 times the original second is y. No dy dx because you didn't differentiate the y part. Plus the original first is 2x times the derivative of the second is dy dx. There you get the dy dx because you did do the derivative of the y part. So that's product rule. And then plus 4y becomes plus 4 dy dx, and the derivative of 15 is 0. At this point, you've done your calculus, everything else is algebra, so keep your dy dx terms together, get everything that doesn't have a dy dx over, so I would have negative 6x and minus 2y off now to the right side, and the 2x dy dx and the 4 dy dx both have dy dx, so I'm going to factor that out and leave behind 2x plus 4. And now to finish this off, to isolate my dy dx, I can divide that 2x plus 4 over to the other side underneath the negative 6x minus 2y. If you want to reduce that fraction, because everybody's got a factor of 2, you can divide everything by 2, but if you didn't and you just left it like this, that's fine. If you move things the opposite way that I did, so that you move the dy dx stuff over, and you left the 6x plus 2y where it was, you have a positive 6x plus 2y on the top, and a negative 2x minus 4 on the bottom, and that's also fine. Any comments, questions with 3? Have you do? Better than the quiz? Great. I did forget to put your extra 2-point bonus for everybody being here on quiz day, but then Chung reminded me to do that, so that's in there now. Thank you. So now your grade in Schoology, not Schoology, on Hack should reflect what you should actually get. Get out the packet from yesterday that we were starting to look at, and I think we finished the pool problem.
Maybe it was left.
Yeah.
Yeah, so we finished the pool problem. We didn't in my other class, so I just wanted to make sure. And that one was really tough. I think on the whole, that's one of the tougher problems. What was more difficult about the pool problem, I think, is that we didn't come right out and say, here's the relationship between like the length and the height of the pool to give you like a ratio that you can substitute. You kind of had to figure that out based on the dimensions of the pool. So sometimes that happens. Usually if there's like a substitution that has to happen, we'll explicitly tell you what that substitution is. Like the height is 3 times the radius. But sometimes it's kind of built in with just telling you the dimensions of this larger shape, and then there's like water filling it up, and the water is going to be a similar shape. It's going to have the same ratio of dimensions. And that's what was going on with the pool. Moving on, we have a distance formula problem. So we'll look at that. I think we're going to do this here on the page, and then I'm going to make up a second one similar to it. So that way you have a little bit of practice for yourself. So let's look at the distance formula problem. This is like number 11 from the homework assignment that's due tomorrow.
The one I didn't get.
The one, yeah. So yeah, you weren't ready for number 11 last night. Up through yesterday, I think 1 through 5 should be doable based on what we've done already, and 7, and 13, and 17 through 20, and then 11 and 31. You might have been able to figure out 31. I'd be impressed for anybody who figured out 11 on their own. So this is a lot like number 11. So our goal is to get through problems like those today in here. But hopefully you've had a chance to look at the homework and you've done a significant part of it, so you're not leaving it all for tonight, because you're going to be hating yourself if you did, because there's a lot. So rate of change between the distance between the origin and a point on the graph of this curve. So I like to draw this so I can have like a visual aid. So I have my graph here, and here's the origin. That's one of my endpoints. And then the graph of x squared minus 2 is going to be what shape? Parabola. And so you have a parabola just shifted down to, so parabola down here, and then looks like this. So we have a point on the curve. We don't know where that point is, so they're giving us very little information. They say you have this curve, there's a point on the curve, it's moving in the side-to-side direction at a speed of 2 centimeters per second to the right. You know it's moving to the right because it's a positive value for that rate of change. So since we're on the curve, we're moving up and to the right. Or maybe we're over here and we're moving down and to the right. But wherever we are, we're a point on the curve moving towards the right at that speed. And we want the distance between that point, wherever it is, and the origin. So what I'm going to do is I'm going to just connect the dots from this point. I'll use this one, and the origin. And we'll call that distance d, the distance. And we're wondering, how is that distance changing? So as the point travels along the curve, how does this distance change between that point and the origin? Any questions with just kind of the scenario and what's going on? So what we need to do is, since we're talking about a distance, probably we'll use the distance formula. So that requires us to know the distance formula. Anybody remember a distance formula? Square root's a good start. What goes in it? So I heard some y, then I heard some x. So I heard a y2 minus y1. That's true. What else? x2 minus x1. True. What happens to each of these parentheses? They get squared. And what happens to these two sets? All right, cool. Now we know our distance formula. That'll be given on a quiz, but you should know it. So you have your distance formula. And then we want to go in and say, okay, well, x2 and x1 and y2 and y1 are all just kind of like very generic things. Let's start putting stuff in. What's one of these 2 points that we know? 0, 0. So since one of our points is 0, 0, point 0, 0, the origin, that can go in for like x1 and y1. And then the other x and y will be actual variables based on the point on the curve. So for this point on the curve, we have an x comma y. So let's fill stuff in. We have the x from the point on the curve. We'll call that x. And we're subtracting 0 because we're connecting this point to the origin. So x minus 0 are the x coordinates. And then you have the y coordinate from the point on the curve. We'll call that y for right now. And that's also connecting back to the origin, so that y coordinate is 0. Any questions with that? Then, what's x minus 0? All right, so we can just say, this is just x squared. And y, this is where the substitution happens. What do we know about y on the curve? It's the same thing as x squared minus 2. So we're going to say, you know what, y? We're going to not call you y anymore. We're going to call you x squared minus 2 because on the curve, that's what y is the same as. And y minus 0 is just y. So it's really just x squared minus 2. 4, 2. And that whole thing's getting squared. So now that's your setup for the distance formula in terms of x. So this is kind of a good place to be. You have your distance formula. It only depends on x. You only have one independent variable. And now what we want to do is get the derivative and figure out d dt. So the goal here is the rate of change of the distance. So the goal is d dt. That's what we want to get. And we're going to get an equation for our answer. We don't have enough information to get like a value for d dt. All we have enough for is getting an equation. We're going to have d dt equals stuck with x. That's the goal here. So with our derivative, our distance equation, we now want to differentiate this. Do you want to differentiate it right now, or do you want to clean up inside first? Let's clean up inside first. So cleaning up inside, we have x squared just chilling. And then what's x squared minus 2 all squared? That's a good start. Minus 4x squared. Plus 4. All right, good. So you do that out, x squared minus 2 all squared, x squared minus 2 times x squared minus 2. If you need to take that off into a back alley, you can do it out there and then bring it back, that's fine. But you should get x to the 4th minus 4x squared plus 4. You can keep cleaning this up a little bit, and you get x to the 4th minus 3x squared plus 4. So all of that is our big D equation. And now we can go ahead and differentiate that. Maybe if you want to write this with an exponent instead of a radical, so all that stuff to the 1/2 power, maybe that'll be better for you for when you go to do your chain rule. And now you're going to take the derivative with respect to time. Time out before we do. Any questions with setup, substitution, cleanup, anything with that so far? Yeah, because that is the distance, and we want the rate of change of the distance. So that's d, we want d dt. So if you do this, you've done wonderful setup work, you haven't done any calculus yet. Any other questions? So now we're finally ready to do like our calculus stuff. What's the derivative of the inside part? 4x to the 3rd. What? Wait, before we move on, what else do we need on this? Dx dt, because we're differentiating with respect to time. And then minus 6x with a dx dt, because we're differentiating an x with respect to time. And that's the end of dn, correct? So all of that is dn. And then what is dn? What do we do with that? Multiply it to d out. So what's d out? I'm running out of space here. So 1/2 times in to the negative 1/2. So let's consolidate this all into just one big fraction. Let's distribute the 1/2 backwards. What do we get for dn then? (2x cubed dx dt minus 3x dx dt). So that takes care of the 1/2 going through there. We can throw in down the stairs and make the exponent positive. And what is in really? Yep. And then all you have left to do is say, hey, we know what dx dt is. So let's take these dx dt's and plug that number in for them. And then we're done. Yes, ma'am.
So, you took a 2 out of the dn, right?
Yeah. So
don't you have to do not have to put it. Oh, 1/2.
Yeah, so 1/2 times those gives you. But then we're going to put a 2 back because that's what dxdt is here. So you take your dxdt and say, hey, that's 2. Plug those in for these dxdt's. That makes it look like squares, so I'm not do that. So these dxdt's are really 2. So then you have 2x cubed times 2 is back to being 4x cubed. But now you don't have the dxdt because that was 2. 3x times dxdt is really 6x. The denominator is set. Maybe turn it back into a radical notation if you want. And you're done. So you're not getting like a specific value for your answer. We don't have enough information for that because we don't know what point you're at on the curve right now. This is just a very generic point on the curve. So you're just saying, hey, here's an equation. You could use that for any point on the curve and find out the rate of change of the distance between the point and the origin. You can still put units on here. So how are we measuring speed earlier? We're going to have the same units because d is just a distance, so that's going to be in centimeters still. Time is still in seconds. And that's it. So you're not getting a value, you're getting an equation for your answer. So that's what number 11 and 12 look like on the homework. Yes? From here to here? So this is where I'm using the fact that dxdt is 2.
Oh,
So I'm taking this and, at the risk of making a mess of this, I plug that in for those dxdt's. Okay. So here?
Yeah.
So you still had 4x to the third?
No, I had 4x to the third minus 6x.
Then you just have the 2 still? Yeah, that would work. And then you could also say, this is 2, the dxdt's are 2, those cancel, and you still end up in the same place. Yeah, but the big deal here is know your distance formula, understand that these 2 points, x comma y and x comma y, one of them is the origin, so those are just zeros, and the other one is a generic point on the curve. Let x be x and substitute for y using the equation. And then it's clean up, differentiate with chain rule, and remembering that when you differentiate an x, you get dxdt, and then clean up some more, and remember, oh, I know what dxdt is, so let's plug that number in. I would recommend do this other one in your notes, like not in the packet, but in your notebook. I'm going to make another problem similar to this, so you guys have a chance to kind of try it for yourself. Would you rather do with cosine x in there, or that enormous mess? Really?
yes.
That would be weird. All right, too late. It's already written down. Once it's written down, it can't be changed. So, never follow that rule. If dxdt equals, call it, all right, so same scenario. dxdt is 3 instead of 2. Your function is y equals cosine x instead of a parabola, but you're doing the same thing. So you have your template there on your page and on the board, and see what you can do with it. Yes?
Are we still doing the origin? Like,
Oh, yeah. Distance between the moving point on the graph and the origin. That's kind of key. Thank you.
yeah.
For a point race, because otherwise this doesn't make any sense. Where did I put my pencil? What's this from?
I would do variable for x 2, 0 for x 1. Same for y. And then you know that y is correct. It's cosine squared.
Would the derivative of that be negative sine squared x?
So it'd be negative 2 sine x cosine x. That's true. Y. Right down. So you have cosine squared x,
Because
right?
it's power.
It's like power change.
Oh,
Right?
okay.
So the inside is cosine x. The outside is
Oh, okay.
cosine squared. So that's acting sneaky chain. So when you have cosine squared x, that's sneaky chain.
So it's just 2
Get rid of the inside. Yeah, so it's negative 2 sine x times cosine x.
times.
Times cosine x. So the derivative of the inside is negative sine. And the derivative of the outside is 2 times the in.
So
Just
then
2
where would
cosine.
we put like dx dt?
At the
There.
anywhere outside of trig functions. So you're right that you'll have dx dt thrown in there.
Put it very end.
You can put it at the very end. Yeah. And then just remember it's outside of all your trig functions. No, okay. You look it over. So it's like this chain rule chain to get the exit. So that's sorry. So you're kind of pushing steps together. So this is your distance away from the D as well. So now you're ready to do that. So that's not this cosine squared x is not the same as 2 sine x. So now you're going to differentiate. So this is the next step. Now taking the so you're looking here to get the differentiating basically. So I think you should try to do it real quick. It's too long. But it's also not the same as cosine squared. So go back up a step and now do the chain rule on the square root of x squared plus cosine squared. So I would maybe rewrite that as x squared plus cosine squared. Inside part is x squared plus cosine squared. The outside is so maybe you take time to write down these else.
So when we put it on half to these, what would I do with cosine?
It's all one, all of the stuff is together. So
Oh,
one
okay.
has to overlap two.
Because the chain rule is like
And then you have sine x and cosine x.
Like you have to take chain or string off.
So the next period, times 2x dx plus 2 cosine x dx. So what's the derivative of cosine? Well, we have the x. So now that's good. Now it's just take that s and add it to this. So yeah, it's good. See, not the worst thing ever. I mean, I'm not saying it's not bad. It's not the worst thing.
I just, when trig is involved, I just can't.
I know everybody sees straight. What's that? Yeah. So the x squared, differentiating that x, he gets the x dt, and then the cosine squared of x, differentiating another x thing there, so that gets you another dx dt. So slap the dx is equal to 2x. Everything else you have there is great. Yes. You, sorry. Yeah. That's good.
Oh no, I don't think. I saw the answer. Like, man, this is the easiest shit.
I hate it. It's, I don't care. I just, it's
So when you go to differentiate cosine squared, it doesn't.
I know it's
So the derivative of cosine is negative sine, and the derivative of something squared is 2 times the sine. So you'll have negative sine times 2 cosine because you're taking.
What am I supposed to respond with?
Yeah, it is.
What did you respond? I didn't respond.
Oh shit. Go.
It says, please respond when you receive the secret.
Oh God, I hope it's gonna be like 4 questions or something.
So you're.
Oh, they said I
Okay, so you said, let's say the square root.
Okay.
If that were all squared, yes, but because each term is
Yeah, like
squared.
number-
no. So
What's
that's
the
like the
1
same
to
as
7?
you know how people.
Exclamation. Yeah. It was.
You think that's fine?
I can do something.
Thank you.
It's the same exact thing. So similarly, if you see this,
Now let me talk to my parents.
I can flunk this stuff. I'll flunk myself.
so what you want to do here now, that you have it set up, is chain rule that whole thing. So inside is square plus cosine. Outside is inside.
Are you taking a science next year?
So unfortunately,
Pluggers, I can flunk it.
Can she, does she have a?
Your eyes just walk out of my eye.
I think she does look out of
So I think you have things set up correctly. So you got the square root.
I knew we were gonna have something else. We had a whole month.
All right, let's go over this. So, distance formula. We have x2 minus x1. Since one of those is 0 because of the origin, what does that end up being for the x stuff? Just x squared, right? x2 minus x1 is x minus 0. That's just x, it's getting squared. Plus, y2 minus y1, same thing. We have y minus 0 is just y, getting squared. And what is y? Cosine x. So we have distance equals cosine x all squared or cosine squared x, like that. That's a distance formula. Any questions with setup? I think walking around, I think pretty much everybody had this that I saw. Now that you have this is now chain rule. I saw a little bit of, hey, let's simplify this, x plus cosine of x. And I wish it were that simple, but it's not. So that's not allowed. So because that's like the same mistake as saying if you have like x plus cosine x all squared and you want to turn that x squared into cosine squared x, also not allowed because what does the exponent really mean? You can't just assume the exponent. You can't just assume the square root. This is not the whole thing in there squared. It's the individual terms are squared. So unfortunately, no. So we have to do chain rule now. The inside part is x squared plus cosine squared x. It might be helpful to think of cosine squared x as bracket around the cosine x, all squared. It's the same thing, but maybe that's a little more clear in terms of what's going on with the cosine x. And the outside, you have the inner part getting square rooted, so raised to the 1/2. So when you go to differentiate, d in, you get 2x and a dx dt. And then you go to differentiate the cosine of x all squared, and that's, I think, what's causing the biggest issues for most people. The derivative of cosine is negative sine x. The derivative of something squared is 2 times the something, so that's 2 cosine x. And along in there, you have to differentiate the x as well, so that gives you a dx dt. So that's what d in looks like. D out, you have 1/2 times the inside to the negative 1/2, and the inside was x squared plus cosine squared x. So now you kind of multiply these things, put them together, and it's just a great big mess. So we would have, that's going to be dx dt, 2x dx dt minus 2 sine x cosine x dx dt. That's your numerator, times this thing gives you a 2 in the denominator from the 1/2, and the x squared plus cosine squared goes downstairs to make the exponent there into a positive 1/2. So that's your answer in terms of doing your chain rule. At this point, it's a matter of canceling out all the 2's and plugging a 3 in for your dx dt's. So for me, the heavy lifting all happens right here, where we take the derivative and put stuff together. Any questions with any of this stuff? All right, so now let's clean up your mess after you're done playing with your toys. 2, 2, and 2 all cancel out. All the terms have a factor of 2. 3 goes in for dx dt, so you have a minus 3x minus 3 sine x cosine x. So that's a 3 and that's a 3. And then the downstairs is x squared plus cosine squared x to the 1/2. Ta-da! Done. So your homework tonight is number 11, similar to the first one, in terms of what the equation is. I think your homework tomorrow night is number 12, which is similar to this one with sine x instead of cosine x, but otherwise the same. I suppose we could have made things a little bit easier and made this the square root of cosine x. And you might be like, how's that easier? Well, when you square root that, then you just get cosine x, not cosine squared x. So, so you might think, oh, a more complicated equation here makes it more difficult, but actually not, because then that's easy to work with. You don't have to draw a graph every time. I drew it for the first time so you can kind of see what the idea is. But once you get the picture, there's the origin connecting to some point on this curve. And this curve is doing what that curve does. Cosine's going to cosine, parabola's going to parabola. Then you can kind of say, okay, well, it's just a distance function problem. Any follow-up with this? All right. Let's scale the difficulty level back a little bit and move into triangle problems. Or I think this scales the difficulty level back a little bit. So the next several problems from today and tomorrow, the rest of this packet really are a variety of triangle problems. And triangle problems really come in basically 3 types. There's Pythagorean theorem triangle problems. There's trig triangle problems, usually involving like one of the angles in the triangle. And there's a overlapping triangle ratio problems, which we'll see at the end to be a shadow problem. I think that's the last one in your packet. So let's start off with, I'm thinking this is a Pythagorean theorem problem. So you've got your airplane is flying overhead, because that's what airplanes do, and you've got this radar tracking station down on the ground, and we want to analyze the straight line distance between the plane and the station. So not the ground distance, the straight line distance. So the plane in the sky, straight line on the diagonal down to the radar station. How is that changing? Or we're telling you how that's changing, so what's the speed of the plane? So for these, all the triangle problems, draw a picture to help you see that it's a triangle. Because you might look at that and say, I don't see anything about a triangle there. So try to draw a picture of this right now for yourself. Take like a minute and draw the plane up in the sky and the radar station down on the ground and the plane not directly over the radar station. Put it off like so. You have your plane and the radar station on an angle to each other so you can make a triangle. And see if you can like kind of fill in onto the triangle the information that you have.
So you differentiate directly inside the square. You're not getting the times the out. You're getting the rest of the inside, leaving only inside the square. So what you want to do is differentiate stuff. Multiply the credit of the big picture outside. So big picture, this is stuff gets square root or something. So you have to get inside. Lines. 1/2 times the inside. That's the so write down ins and outs that I've gone before about the city. How
You don't have to run very much.
oh I gotta differentiate the inside part. So I gotta differentiate the outside part. So and then I put the other ones like alright, so once you're here I would recommend right now in equals x squared plus x plus squared. Now equals inside.
All right. So we don't get it. Where do planes go? In the sky. So we'll say this is our sky. We'll put a plane up here.
I'm not fine with that.
All right. So that's our plane. Where's the radar tracking station?
At the bottom of the ground.
On the ground, because that way the plane can go over it. So you have your radar tracking station on the ground. There. Here's the ground. The plane is moving so that it's going to go over the radar tracking station. We have a straight line distance between the plane and the station. What do straight lines look like? And lines. So we draw a straight line between the plane and the radar tracking station. And we call that distance S because the straight line distance between the plane and the station S. S is referring to the straight line distance. So that's S. We tell you how that's decreasing, and we tell you what S is. So we give you a lot of stuff about S, the distance directly from the plane down to the tracking station. And then we want to know what's the speed of the plane. So if we just continue this arrow here for the speed of the plane, or the direction of the plane, it's moving like this, till it's right over top of the radar tracking station, and then you can draw a vertical line here. We'll assume that the plane is flying horizontal. Yeah, so if the plane is moving this direction towards the tracking station, then S will be getting smaller, right? Because eventually, when the plane is right over top of here, S will be the vertical height, and that's going to be a smaller number than the hypotenuse, right? So we now have this right triangle. We have the vertical line straight up from the radar tracking station, with the horizontal line that represents the flight path of the plane. So assume that the plane is flying on a horizontal trajectory. And then we've got the diagonal line that connects these two items. So that's our picture. This is a right angle. And we need to have variables for the other two sides of this. I like to use an X and Y, and X I like to be horizontal, and Y I like to be vertical. And then we have, well, which of these things is changing over time? So is the x distance of this triangle changing? Yes. So we'll have an x and we'll have a dx dt. Because x is a variable, and we know it's a variable because as the plane continues to fly, that distance changes, so dx dt is changing. Is y changing? No. Because it's a straight line. So since the plane is flying on a horizontal path, its height does not change. Y just represents the height of the plane. So height of plane. I'm feeling like I probably should have told you that information as what is the height of the plane. So, yeah. Should be in here. By the way, the plane is 6 miles up. So let's put that there. By the way, plane's altitude is 6 miles. Kind of key information. And then we have S. What do we know about S? It's decreasing, so that tells us ds dt. How fast is S decreasing? 400 miles per hour. So ds dt is 400 miles per hour. Now, since it's decreasing, is that a positive or negative 400? Negative. So technically, that's a negative 400. And what is S right now? 10. So S is 10 miles. And the S is changing at a rate of 400 miles per hour. And it's decreasing, so it's a negative 400. So that's all of our information. What equation can we use to relate the 3 sides of our right triangle? Pythagorean theorem. So this is a Pythagorean theorem problem. So you look at your thing and say, I've got a right triangle. And I'm talking about the sides of the right triangle, Pythagorean theorem. So on a lot of these triangle problems, if you're just talking about the sides of the triangle, it's a Pythagorean theorem problem. And so we have x squared plus y squared equals s squared. Y squared is a constant. Because the height of the plane is always 6 miles, so we can take out y and say, we'll just put a 6 in there. So x squared plus 6 squared is 36, equals s squared. And so that's our initial equation. And then what do we do with that? Differentiate. So you take the derivative of this. What's the derivative of x squared? 2x dx dt. What's the derivative of 36? 0 goes poof. What's the derivative of s squared? 2s ds dt. And so now you have these 2 equations. Our goal is to find out dx dt. We want to find the speed of the plane. That's how fast it's moving horizontally. So we'll fill stuff in down here, and if there's a piece of information that's missing, we'll go back up to the Pythagorean theorem, solve that, and bring it back down here.
Why did you plug in a 10 for S?
Because that is changing. So they give us a number for S, but they also tell us how it's changing, so we know that that's not a fixed number, that's a variable. So we'll have to use that 10, but we don't want to plug a 10 in here the way we do for the y. Yes?
Why is y staying the same? Because if it's decreasing and it's moving to the left, wouldn't it be going down?
So S is decreasing, but Y is not. So
Yeah.
the plane isn't going down. The plane is continuing to fly horizontally.
But
S is decreasing because the horizontal component of this line is shrinking. So like this, the diagonal has an upwards component and a sideways component. You guys, have you taken physics? Okay. If you have taken physics, you remember vectors?
yeah.
The i's and the j's?
Yeah.
So the x distance is all i's, and the y distance is all j's. X is sum of both. So as the plane travels, this S distance is going to shrink as it becomes more and more like Y. Because you're taking away the horizontal distance and you're making it all vertical. But the plane is always at a height, like the plane is always flying up here. It's not, the plane itself is not going up or down. So that's why the Y is a constant. So at this point, you would fill information in down here. You would see, oh, I don't know what X is right now. Plug 10 in your Pythagorean theorem, solve X, and then you'll be able to solve. So we'll return to this tomorrow. At this point, you should be able to do the homework. We'll go over questions in the homework. We'll go over more of this tomorrow. You'll have more homework to do on Friday from the packet, not from the packet, from the textbook. And we'll be doing more of these problems all week. See you.
Yeah, because we're still able.